going over homework 5, which is the MPI Matrix Multiplication. For this assignment, we're going to be writing a sequential and parallel functions using the MPI, and we're just going to be performing the matrix multiplication. So we're going to get matrix A, which is size of n times 32, and a matrix B, which is 32 times n, and we're going to get the result of matrix C, n times n, which is the size. And so here we're going to be writing the serial or the sequential version of this, which we're going to call serial, and then the parallel function of this. And with the parallel, there's three types that we're going to be using that differ in communication. One is the blocking P2P, collective communication, and non-blocking P2P. Okay, and at the end of this, we're going to be trying to prove the theoretical time complexity of O(n) squared. So that is that. I'm going to show you the execution of it, of what it would look like. So here we're going to take this, and we're going to be running the main and serial. So serial doesn't have a main method, so we created a class or a file that has the main. So it's going to be using that. Sorry, I have to do module load open MPI. Okay, now. Okay, and then I'm just going to run one process because it's serial. Okay, so this is what we got. Our default of n is 512, and we only have one process, and the time that it takes to execute it was 0.006 seconds. And we checked that. I'll show you what the C underscore check implies, but yes, it was equal to the serial result. So now if we do this, and with this command, we're going to be using the block file and the serial, and then compare the two and allow the block to use 4 processors. Okay, and so you can see already, so again, we use 512. Now, if we wanted to use a different number instead of 512, we want to do like, I don't know, 1024 as a number, then we can specify in the command prompt, but I just want to keep it consistent amongst all of them, so I'm just going to keep it at 512, but include we specify 512. And so now that we use 4 processes, comparing to the block, it was 0.003. Comparing to the 0, it was 0.007. So already the non-block, which is the parallel version of calculating the matrix, ran a lot faster than 0, which is to be expected. And we used 4 processors. I mean, let's just say we go ahead and start modifying the 4 to an 8. Now you can see that it even got faster. See, now it's 0.003 for 4, and then for this one it's 0.002. But again, pretty much serial, right? It's running at the same time. It's not using processes. Now let's go crazy and do 16. Here we might see some tapering off. So it ran a little bit slower than compared to the 8. So we can say maybe around between 8 to 16 processes, where running more processes may not be as beneficial. Now, if we were to do the block, let's go play with this guy and run with 4 processes. So if we compare, it's 0.002. Let's see, with this guy when we run 4, so you can already see the non-blocking beats blocking, which is great. But now let's go ahead and compare. If we let's do 8. And we can see it already beat all of them, because we remember that last time blocking when we ran 8, it was 0.002, and this one is already 0.0016. We rounded to 17. So that's even faster, which is crazy. So we can see that it ran 0.616. Okay, so that's pretty impressive. But now let's go ahead and try collective. Sorry. There we go. Let's do 4. Okay, so collective was slightly better than blocking, but not as good as non-blocking. And then let's do 8. Okay, so it did well compared to blocking, but actually was slower than compared to non-blocking. So already we can already see non-blocking is the best one. Um, and so we're going to go ahead and go over the actual code. So for the main, um, the serial is using the mains file for the main function. So for the serial, we're just gonna we're gonna do the multiplication serial where we're gonna take each row. This takes the um, each row from A and the column from B, and then we're gonna go ahead and compute the dot product, which will help us out to create the matrix of C. And so the idea of it is that once we've looped through each one, we've collected the sum, and then once we've computed it, we store into the sum. So now all the sum, we're going to go ahead and store it for each individual C's elements of the matrix. So that's what this is doing. And the is equal, this is pretty much the same for all of them. We're going to be using this is equal method, where it just checks, hey, does the two matrices that we got from doing serial versus its respective comparison match all the elements? If not, then return 0. If so, true. If so, return 1. Um, and so for the main, basically, here we this is where I actually you know call those certain method that's needed for the serial. So we have the inner dimension already set to 32 because that's what was stated in the assignment. And then here we're going to go ahead and get started for the MPI. We're going to set rank to 0 and size to 1. And this is us getting our ranks and sizes. And this is us setting the end of matrix to 552, or sorry, 512. But we can overwrite this in the command, and that's fine. And this is us getting that if someone were to put that in the command prompt. And then so if there's only one rank, which would be by default set to 0 since that's what we'd set it to, go ahead and first calculate the respective size of each matrices, where A is going to have n times 32, B is going to have 32 times n, and then C is going to have n times n. This is what was given in the prompt. So I didn't make that up. And then we're going to go ahead and allocate those matrices and then fill them up with random numbers between 0 and 1. And here is where we start the time of it being serialized to multiply the matrices together. And then this is the end time. And then this is us calling that serial, so we can go ahead and get that. And then in this, this is just a little sanity check to make sure that all some of the elements are stored into the sum. And then we're going to check to see if this C underscore check is the same as what we have just calculated. And so what's going to print out is the n, which is the right here, the size of the matrix, which is 512, and then number of processes, which in this case its serial will be 1, prints its serial's time, and then when we subtract n minus start, it's going to tell us what was the time it took for the serial. And then was it equal? It's going to say yes or no. So this is a ternary operator. And then we're going to freeze some resources. For this, if we look back at the assignment here, what we gathered from that is it was basically the serial time is 0.006, which has the most speed up and efficiency being 1. Now we're going to use serial as the baseline, and now we're going to be comparing the parallel times, or the parallel execution methods, for both blocking, non-blocking, and collectives. So for blocking, non-blocking, collectives, we're going to have increasing number of processes, which would be 4, 8, and 6. And then over the course of the code, I will explain how we're executing blocking, non-blocking, collective, and then we're gonna go over its results. I went ahead and graphed it just to show you whether the parallelization did perform or did not perform better than 0, and that is to be continued. Now we're going to be going over the code for blocking. Okay, so for the blocking file, um, the blocking point-to-point communication, we're going to be using a couple of methods. We're going to be using MPI underscore send and also MPI underscore receive V. So first of all, before diving into the code, I'll just explain how blocking works. Um, so with the MPI underscore send method, it waits until the message has been set or safely copied out of like the send buffer before moving on to the next line of code. So when using the MPI receive V, it waits until that data has been fully received. So how does it affect with our code? It's just that the way we communicate data and do the computations, all that happens sequentially. So that just means that one must finish before the other starts. So this is supposed to, unfortunately, it does allow processes to sit and wait a bit and not do anything until they get the data that they need. So but in our example, we have something called like rank 0. It sends like a slice of matrix A and the full matrix of B to each of the process using that MPI underscore send. And it waits for those and sends to finish before continuing. So each of the processes also have to wait to receive the data before computing. So in terms of performance, though, blocking communication is kind of easy to implement. It's a little bit slower, which we'll see later, but let's go ahead and dive into the code. So here we just have the inner dimensions of the matrix. In the main, we called a few things. So this right here is just us declaring some stuff for the serial functions that is needed for us to compare for the serial and block. So this MPI init, we just initialize the MPI environment. We have the rank set to 0 in size. We're getting those set rank and size. We have the n to be 5. This is pretty much the same as serial method, which is we set the default to 512. Can be overwritten if we wanted to in the terminal. And then we have something tags in here, and then which just it's a form of like helps us to debug to see like what got what message between the two processes. You can do without or with it, doesn't really matter. And so each of the matrix will have a different size calculated. Same thing with the serial, so pretty much I'll skip that. And so counts and dispels, this is basically we're going to allocate memory to each and one of those. It's similar to what we've done in class. And so dispels is just displacement, and then the counts, which is counting the elements in the matrix. So here is us, we're splitting the number of rows per sizes for each of the processes. So we just take the base, which is like the number of rows for each rank will get, and then we just do a modulo of n with the size, and whatever leftover rows occur, then they get distributed to different processes. We're just trying to balance as much as we can. And then whatever, we set the offset to 0, but you'll soon see right here is when we actually do the row partition. And so it computes like the number of rows that each of the matrix A's and C gets for each of the ranks. And so this is, like I said, taking care of the uneven splits that occur. So it just does a for loop for each of the processes. Here it just takes the first remainder of the ranks and gets the extra row. And then here we're just storing that the start of the row index for the rank and dispels process. So, and here we're just updating the adding it to the offset. After we complete that for loop, we are going to soon instantiate these matrices, and these are the full versions of A, B, and C. Remember we were talking about the slices of matrix A, but here we're going to be working with full A, B, and C. And then here is a block just only dealing with the main rank, aka rank 0. And so here we're just going to be only working with full matrices. Here we're actually allocating memory to those matrices, filling them up with random numbers from between 0 and 1. And then here we're actually going to start performing our block. So we're going to start the time. And then we're going to actually assess, and we're going to send each worker its row count, its slice A, and its full B matrix. That's what this for loop is doing here. And this is where we're sending that information to each of the worker processes. And then we're making sure we are sending that information, yes, like I said. Okay, now if let's say the root computes its own rows, then while sending them, we're gonna go ahead and take care of this part, where here is just we're skipping this one. We're just gonna skip the first row of an A, and this is where each of the row case is actually pointing to specifically the first row of A and the first element of ranks A of block A. And this is doing the same thing with C. And then now this whole for loop, the point of this for loop is just supposed to compute the ranks 0, its own rows of the result of the matrix C. So here we're actually performing, so first the outer loop, what is it doing? It loops over I, just so we can get to the local rows of A and C. Now the middle one, what it's supposed to do is it actually loops over J, so you can get the column of the C. But the innermost for loop, what it actually does is actually performs the product, the dot product dimension, and this is us actively doing the multiplications of getting row A, the first row in matrix A, and but then multiplying it with each element with the full matrix of B, and then we're after doing we're attaching the value and updating it. We're going to multiply and then store into the sum. After computing that, then we're going to update the C matrix. This is us actively filling in that C matrix, and we're going to just keep doing that until we fill up the C matrix. Once we get out of that, we're going to go here. For this for loop, it just concerns with collecting just the rank 0's results from each of the workers' processes of their rows, and then we're going to take all of their little slivers of their output of matrices, combine it so we can create the full matrix of C. And then this is where we calculate the stop, we calculate the block time, and soon enough we're gonna have a print statement that prints the block time. So here this is us allocating some memory for C, and for serial, and we're gonna compare to C. Now this is the actual comparison to see if we're on the main rank. Then what we're gonna do is use block method, and then we're gonna go ahead and print the statements that it needs to print, which is, hey, what end did we end up using? Did we use a default? Is it 512? Okay. If not, take the user's input, and then here's the number of processes that's going to print, the non-block time, the serial time, and then finally we're going to see if if the calculations that block performed was equal to the serial, and it will return yes and no. And as you saw, like all of the outputs, it was true that it did calculate, so that's great. And then it's going to free up the memory. Now in the case if it's not working with rank 0 and it's just a worker doing all of it, the work, then this is what the worker process is going to do. It's going to have the row count 0, okay, and then we're going to go ahead and, well, first of all, the worker row count, that's just, we want to tell the worker process like how many rows it's going to be owning. And so this is the receiving part, because remember, we already did all the sending, we haven't received it, so this is the worker receiving its workload. And then if in the case that there is work, then let's go ahead and start doing this, which here, this is our local buffers, fairly similar to how we have it in class, where basically it takes the rows of that specific matrix, depending on A, B, or C, and then where the rank owns that letter. So depending on if like the local row is like greater than 0, then it will actually allocate the size that it actually needs to be assigned. And so here, once we receive information from rank 0, then we're going to go into this for loop. And this is how we just compute the sliver of the matrices of C, and then it stores them and then updates it here. Okay, and then once we're done, we're going to go ahead and send it back to rank 0 and then free up the memory, the one that it's used. So A local, B local, C local. And then after that, we're just going to free up some more memory, and then we're just going to close it out. So that's pretty much what C is. And you're going to see, like I mentioned, like the preparing the for each parallelized execution method is pretty much similar, so I'm not going to repeat it for non-block and collective. So let's go ahead and go back up. So again, I'm going to just briefly explain what non-block is before diving into the code. That way it makes a little bit more sense. So for like non-block, the way it works, it actually starts with using starts like a send or receive without waiting for it to complete. So instead of like the process continues to execute like the other workers, so like us computing the matrices, it's gonna do some data transfer to the background. So that means while one process is doing the computations, it doesn't have to wait. It can go ahead and do something else in the meantime. So, but at the end of it, we can just call like a method, like I think we use like MPI underscore wait. I think I have to use wait all, and I'll flag it to show you guys. But basically, we are going to use that wait method just so we can ensure that the communication has finished before using the data. So how does that like affect our code? Is that it allows like communication and overlaps and computation overlaps. So it reduces idle time, which is really great in terms of like parallelization, and it improves performance. So while data is like being sent or received, the processor can like compute its own row of the matrix. So later on, you're going to see in our example or in our code that when rank 0 is used, the MPI isend to each of the process, it takes a slice of A and the full of B, just like how block did, and then immediately starts computing its own portions while transferring that data to the other workers. It's still in progress. So what does that mean? Basically, the performance is going to be faster, ideally faster than blocking, right? Because it's less idle time, and it hides that communication time behind the computation. So it's really good and makes it improve performance. But let's see how that's being implemented in code. So again, pretty much similar to how we started. Yes, we initialized MPI runtime. We set rank to 0, size to 1. Okay, pretty much the same. I'm going to just kind of skip over this because it's nothing new. Here, now we're going to start the non-blocking section. So start time. Hey, are we in the master rank or the rank 0 or root? Okay, if so, let's go into it. And in this for loop, we're just going to let each worker know that how many rows it owns. And this is just me doing a preventative measure. Just want to see, just like, this is like blocking, I know, but this is just a debugging portion of it. So no worries there. But, and it could be totally skipped. So here, I had to make sure I send like 2 the buffers per worker, so that way they can get the entire B and the worker's A. And so this is how I basically send that request to each of the workers. And then, so this for loop, this is just me sending the data that it needs to each of the workers. And to do that, we noticed that send index gets increment, and that's how it proceeds for each of the process index. So that's great. Now that we're now again, we're still in the root. So in the root, we're going to take the first the root has to do some computations too, right? So here we're going to do the computation of its own row, and then we're still sending out those data transfers in the background, remember. Okay, Same thing, kind of what we did before. Here's us computing matrix C. And then now here is us receiving, all the MPI requests from each of the worker. And then what we're going to do is that we're going to count how many of these like IREC V requests that we actually got. And then we're going to loop through each worker for each of the rows. So here is where rank 0 actually is posting like non-blocking receives to each of the worker processes block of the result of matrix. So then at the end of it, we can all put it together and get the full matrix C. Okay, so this is us creating that non-blocking and getting all the information from each of the workers. So, and I wrote a side note here that this portion is just, it starts with the row index and the global C for the workers row. So here is us waiting for all of the non-blocking operations. So I used here like the wait all, and then same thing we're doing for the request, and then we're freeing up those respective memories. Now we're not in the rank, and this is workers processes work. It starts here where first the worker receives the information that it needs to know, so it needs to learn how many rows it owns, and then if there is a worker row count, then it needs to do the buffer. Hey, you need to go ahead and once you receive all the inputs that it needs for B and a slice of A, and remember, all of this is done asynchronously. Blocking does synchronously, but here's asynchronously. Okay? After we get all the information, we're gonna wait and wait for all the receive requests and everything like that. But meanwhile, while we wait, we can go ahead and start computing our portion of C. Same method that we did in block, which I'm going to skip over. Freeing up memory. Here we're starting the block time. We're actually calculating the block time. And then now that we're back into rank 0, then let's go ahead and start comparing the serial and the non-block. And this is pretty much the same thing, where it's going to print the n, the number of processes, the time, and serial. Check if non-block was equal to the serial's matrix C's output. Free up some memory. There you go. So now we're going to go talk about the collective communication. So again, I like to give them information a little bit before talking the code. So how does it work? Well, collective communication involves like all the process in a communicator. So it uses a built-in MPI routines that basically automatically coordinate, the data movement. So like, for example, you're going to see later on, I use MPI underscore bcast, which is broadcast, and it sends the same data like matrix B from one process to all the others at once. So while it's using the two methods that is MPI scatter V and MPI gather V, just to divide and gather the data ranks among the ranks like efficiently. So how does this affect our code? Well, the idea of it's supposed to like simplify the code a little bit, so we don't have to actually manually do the loops between the sends and the RV calls, which you've seen in non-block. But here we didn't have to do that. So MPI can internally just optimize that data transfer without us piping in, which is great. So like the point of those three methods that I mentioned is like with the broadcast, that shares matrix B to all the processes because every single one of them needs matrix B. Scatter helps distribute the rows of the A to among the different processes. So like each process can compute its like local result. And then the gather helps to collect all the pieces of C and then give it to rank 0 so it can get the full matrix of C. So it's supposed to improve performance. So we'll compare whether if it beats like non-blocking, because we already knew non-blocking is going to beat blocking, but let's check later if non-blocking gets beat by collective or not. Okay. So let's go ahead and dive straight in. So basically same part. I'm just going to go into the part that's different. So same. Okay, if you're rank 0, go ahead and allocate. Random, fill it in. Okay, local. So in right here, our local buffers. So if here we're going to allocate the A slice only if there are rows. And then here, everyone gets B, like I've mentioned, right? But then here we only allocate like a slice of C. And here we are attaching, we're creating count A, dispel A, count C, dispel C. Everyone gets B, remember. And so here it's important to note that since we're building, the scatter and the gather needs these specific counts and displacements in the number of elements, and also the partition's gonna need later, just so we can convert them all into an element based arrays. So that's what we're doing here. We're multiplying and updating their accounts A. This is the array that we were talking about, and this is where we're starting the time for collective. And then say, hey, if you're rank 0, can you go ahead and start broadcasting B to everyone else? If not, then go ahead and you don't have to do that. You just have to use, everyone has to get full B, and then but if it's not, then just use your local B. That's what that's doing. And so with scatter V, it helps us scatter like the rows A, where the rows is multiplied by the k floats to each of the rank. Now scatter requires buffer counts and displacement, and the type of sense is what basically is what I'm saying right here. It's what it needs all this just so it can scatter its respective thing. And then, hey, if we're still calculating the local buffer C, this is how we're doing it. Hey, is there local rows? If so, then, or if it's greater than 0, then do this where it's checking to see which B we get. Is it the full one or is it local? Regardless, go ahead and just loop through each of the rows and columns, and then go ahead and calculate its respective matrix C. Now finally, we can go ahead and gather all the partition rows from row C, put them together, and then give it to rank 0 so it can get the full matrix C. So in rank 0, this is what we just do comparison of the number of the comparison of really time and whether we got the matrix C to be the same in collective and 0. And then we just free up memory. Now it is the same, which I will now show you the results of what I found to be. So we found that overall so remember, serial was the baseline. We found that actually non-blocking was the best performing in terms of speed up and efficiency. The more that we've increased the processes, the less time it took to execute them, which is good because it is improving the performance. We know it's improving performance because two things. One, we're comparing to the serial time, and also we can take a look at the speed up and efficiency. Now, I did notice that collectives performed a little it did beat blocking. Blocking was the worst one, especially if you go from 8 processes to 16, because if you take a look, it goes 43 and it jumped down to 19, but there wasn't that much of a jump when you compare it to the other processes with other parallelized methods at the high number of processes of 16. And then if you take a look at the graph overall, so you remember, as you increase the number of processes, at one point processes are not going to get faster than it is. So what's going to happen is that once you increase the number of processes, parallelization can only improve so much. However, you do want to see a slight decrease, and this basically shows that it's computing faster because it's taking less time. And overall, you're seeing by a long shot that non-blocking really beats both blocking and collectives. So, and then overall, I just wanted to say that we said the time complexity of this is going to be O(n) squared, which proven the case because to remember to perform like the dot product for the matrix multiplication, there's going to be like 32 multiplication and additions, and the size of matrix C is n times n, if you remember. So that gives like the inner dimension having a constant of 32, which we shown in that in code, and the total, which basically means the total work gross is proportional to n squared. So it does, in fact, back up the theoretical time complexity. Thank you.